we have an eminent personality from a research center, PM Abdul Rahiman, scientist E. He graduated from REC Calicut in 1987 and MTech from REC Bhopal in 1998. He joined Central Water and Power Research Station Pune in 1992. After a brief stint in Fluid Control Research Institute, Palakkad, he has worked for Kuwait University of Engineering and Petroleum for a brief period in later of 1992. His field of specialization is prototype and model testing of hydro turbines. He has vast experience in laboratory testing of pumps and site testing of turbines and flow meters. He has also handled problems related to pumping systems, pipeline optimization, and pump intake studies. He has more than 80 papers in various national and international journals and other technical during his 3 decades of professional experience in hydraulics. So I hand over this session to Abdul Rahiman sir. Sir, please. Sir, you are mute. Okay.
I can't hear, sir.
Thank you so much, Professor Swaraj. I'm trying a parallel. Good afternoon, everyone. I'm extremely sorry being delayed by good time. First of all, I thank the organizers having deposited some faith in me. I don't know, my good experience is in site field studies related to turbine, pumps, and flow measurement. I don't know how it will be accepted by the August audience here. I'm made to believe that the August audience is the masters of fluid dynamics. I'm a student of this subject here. Hopefully, we will have a live interactions. But I'm looking for this opportunity as a learner than a teacher. I would welcome a lucid discussion between the participants and the humble dealer here. In our presentation, I have divided the presentation into 2 halves. One is dealing with turbines and the other one on pumps. At present, we will discuss on critical aspects of operation of hydraulic turbines. We know the basic components of conventional hydro power plants. I don't discuss in detail. This PDF is shared to the organizer. You can have it later on. This is the main component of hydro power plant: reservoir, dam, in whatever name it is called, penstock, associated gates, intake gates, then main inlet valve is also there, then the turbine, the core of the system, then generators, transmission systems, and tail race outflow. How a hydro power plant works: reservoir is there, turbine is there, power, and associated with each, what we are concerned is the flow, that is discharge, that is the supplier is reservoir. Turbine, the core component of aiding generation of power, it is integral with the generator, where we get output in the form of, say, megawatt power. Okay, this is depicted in this slide. Next is the heart of the system, the runner. The size of hydropower plants are large power plants above 100 megawatt. We know the many power plants like what we have in Idukki and many other places. Then medium capacity above 5 megawatt is so called mini. Up to 5 megawatt is it required a correction. Small up to 5 megawatt is called small. Then there are micro hydropower plants that is very simple to operate with the local technology. Typical pump storage system is like this. We have upper reservoir, the penstock, turbine, which can also be used as a pump, and it is going to a lower reservoir. In seasons when there is no much demand for power generation, power of the grid is utilized to work the turbine as a pump, and reverse happens. Okay, reverse happens where water is taken from the lower basin to lift up water to the upper basin, where it is stored in the something like a battery cell. It can be reused in when the power is in big demand. Okay, this is a world scenario power generation. Ever increasing business and will cross over 50,000 megawatt per in next 20 years. These are all the projections. The power potential is very good in India, but the generation cost of implementation of a hydropower plant is a big hitch, and it was fastly going on during the initial fire plants. Maybe perhaps during the region of what we can say Nehruvian era, but later on it has lost its pace and impetus was given to thermal power plants. Now the situation is that lot of money is put into thermal scenario, and we can't come back from that scenario because most of the power generation is taken in a economic scenario where taking back from such thermal generation trend, taking back from that trend will ultimately lead to losses, because most of the mega projects are implemented with the large number of funds poured into this system in the form of, say, loan from World Bank, etc. So that situation cannot be negotiated or taken back. So, hence, otherwise, whatever the plans done for thermal generation will be a utter loss. Hydro, the biggest disadvantage associated with the hydropower plant is that it takes a gestation period is too large. It takes years. Maybe 10 to 20 years, and the problems associated with this kind of hydropower plant is that it should be accessed by the immediate vicinity in the society adjacent to the scheme. So there are so many environmental issues in implementation of large mega hydropower plants. So now the avenue is that we have to concentrate much on other non-conventional energy sources like wind, solar, etc. And the story is very good, encouraging, and we are moving in an encouraging phase in this scenario. So as I discussed, these are the positive and negatives of pros and cons of hydropower plants. I think I need not have to discuss in detail. It is environment friendly, it is renewable. As you see nowadays also that water is poured in plenty to the level of a catastrophic scenario, and that is the story of Kerala. We had a very, very bad flood in this same month, maybe August 2-3 years back. So what is always available, it is only an issue of storage and usage for the benefit of human community. Basically, most of the hydropower plants are used for base load plants as well as peaking plants. There are many plants, peaking plants, because it is very easy to start and stop with it in a matter of minutes. We can start a hydro plant and switch off. So it is always used as a peaking plant. But in where water is available abundantly, as in Koina hydropower plants, this kind of hydros are used as base plants also. In a 24-hour, one-day situation, any peak load demand can be accepted by a hydroelectric plant very easily. And the cost of operating hydropower plant is very, very minimal, and use itself is beneficial to other scenarios like agriculture in the downstream. This is the type of one picture, an envelope showing the range of operation of axial, Francis, and Pelton type of turbines. Classification of fluid machines is impulse type of turbines, reaction type of turbines, and propeller type of turbines. Impulse, the potential energy is used, converted, and the exit is in atmospheric, and the efficiency range expected is also a lower range compared to other these two major families. And operation very easy. There are many sub-classifications among these Pelton turbine impulse type of turbines, like single jet, multi-jet, etc. Mounting, horizontal, vertical. Then reaction type of turbine is good for a very good, reasonable efficiency in the range of above 95% for a turbine, and it can be used in a huge range of applications, head ranges. Now the trend is to use the Francis type of turbines even in the range of Pelton type of turbines used earlier. Then the axial type of turbines are used for catering for low head but high discharge. Here one may ask why this kind of different type of turbines in say Francis to shift to axial. Mainly cavitation aspect makes this change, because for even higher discharge and also lower discharge, these regimes, this Francis type of turbine is attuned to have a phenomenon called cavitation, that is boiling of water, lower pressure regimes. But the turbine is axial, that is also not absent. Cavitation phenomena is not absent in axial type of turbines, but here one can see that the more of area, annulus area is covered in axial type of turbines, so an average low, average and moderate velocity can be expected in this large modulus of this one. So cavitation is to an extent it is controlled. So this is a schematic of a Francis type of turbine, Kaplan type of turbine, then Pelton wheel. This is the range of head. Now I will discuss what we in CWPRS is doing related to hydro turbines. We are not the designers of turbines. We are the what we can say is a neutral agency for acceptance of turbine plant. Acceptance test is required for guarantee verification of efficiency during plant commissioning. It is an absolute test. For example, any say a project like a Kutyadi may go for global tenders for commissioning of a hydropower plants, and there may be a global bidding, and say among turbine manufacturers, anybody may quote, and the competitive bidder will fetch an order for supplying a turbine. There will be so many claims of as regards efficiency, cost, etc. And those, it is likely that those who has offered highest efficiency and lowest cost is likely to fetch a order. But once this is done, it is the absolute necessity by the purchaser, like KCBL, to ensure that this guarantee is met. Otherwise, there will be a heavy penalty losses for the manufacturer having failed in meeting the guarantee. Here, a role of a neutral agency like CWPR is very important. We, along with both the manufacturer or what we say supplier of a turbine and the purchaser of a turbine, we come in between them and see that the guarantee is met at the field, at the commissioning site. This is a very difficult task because we can't always rely on the very standard methods for measurement of flow. Had it is possible, and power generation, we can in a new plant, it is not a big issue. We can depend on the high quality instrumentation supplied at a new plant with the factory calibration. Here, the flow measurement is always a big challenge because we can't have a extra arrangement for measurement of discharge in a standard scenario. So sometimes the penstock is buried in rock or in concrete. Sometimes it is not at all accessible. Sometimes it is accessible, but standard length like upstream and downstream length for a flow meter to be used is not met. So there is really a good compromise that is need to be made at a actual practical site than in a laboratory. So the CWPR is called upon to take such a third party judicial like scenario where an acceptance by the purchaser is to be ensured. We have done this kind of role in Loktak hydroelectric power plant in Loktak, recently in Chiplama, that is last year November, for near Hirakud, Chiplama hydropower station, etc. And Salal hydroelectric in Jammu and Kashmir, etc. To identify, then this is one scenario I discussed, acceptance test. Another one is in a old plant, say, usually any component, civil components of hydroelectric plant like pipeline, then all concrete structures, dam, all this, because pipe is also clubbed under civil component. They all have almost a life of 100 years. But mechanical, electromechanical components like turbine, then draft tube, then generator, valves, guide vane, this kind of thing, parts of hydropower can be assumed to have a life of 35 to 40 years only. And a big review is required after a life of, say, 40 years. And we have to see which turbine is having some trouble in after a long life of operation, and we have to look for RMU, renovation, modernization, upgradation of plants. And as a pre-runner for this kind of activities, we need to identify parts, identify turbines which need immediate attention. So for this purpose also we need to do hydro performance test. Then in the initial power plant also we can have some troubles we have, as a purpose of troubleshooting, we need to do this kind of investigative studies on hydraulic performance. Then after use of a long service, we have to re-rate the turbine. Sometimes upgradation is possible, sometimes this lowering the specification is possible, and we may have to retrofitting of turbine is required in a same scroll casing to meet the actually what is in tandem with the existence of the site. So then there are tests mainly concentrated on extent of efficiency improvement that is possible, because improvement in efficiency is equivalent to generation of good amount of power. Then to optimize use of quantum of water, we can use this kind of tool of site performance tests. To solve operational problems, evaluation of machine performance needed to solve operational problems like machine operation, excess cooling, water consumption, etc., etc. IEC 641 governs the method for testing turbine at site for acceptance or index tests. Three major parameters required to be measured are output power, net head, and on turbine, and turbine discharge. Three. One is output power, net head, turbine. Here, power is easy, head is also easy, but discharge is always a challenge for measurement of discharge. During prototype hydro turbine test, flow measurement takes a critical role, calling for accurate and reliable value during stable operation of turbine. Among few available flow measurement methods, the pressure time or Gibson method is also very well-known method. Winter Kennedy measuring system is another scheme generally used during field tests if arrangement for pressure tapping across turbine score is implemented during commissioning. This kind of equipment apparatus is done in Chipilama power plant. Recently we have conducted. There it is something like, you must have seen what is that? Venturi meter, nozzle meter. Difference of pressure between one tapping and another tapping is the measure of discharge. Same way, in a scroll casing, two high pressure and low pressure tappings are selected. That pressure is monitored, and that gives the discharge. But for this, for a running plant, it can't be done because it is to be connected to scroll. So it has to be done during commissioning. Okay. Hope I am audible, right? You are with me?
Yes, audible. Please continue.
Okay. Measurement of net head across turbine, as you know, it is very, you are all teachers of fluid mechanics. It is a well-known Bernoulli's theorem that is, we can relate it to SFE, steady flow energy equation, or whatever name it is called, steady state energy equation. It is total head-on acting on the net head across the turbine is the difference between these two energies, that is P by gamma V square by 2G plus Z measured at upstream and downstream. Upstream is immediate upstream of scroll, that is near to main inlet wall, and downstream point 2 is usually end of draft tube at seen here. So we have to measure three parameters here: pressure, velocity, and datum difference. Here pressure we can measure easily, and in P2 pressure is absolute zero. It is atmospheric, open to atmospheric. Velocity, we discharge you measure, then area you divide the penstock area, and here area of the draft tube you divide, we get V2. So this is the formula. and this is only for head. And for discharge measurement, say like a pitot tube, we can't use it. We can't drill a hole. It was done in some places. For that, shutdown is required. So, and we should be very careful about traversing a pitot tube across a penstock, which is having very good high velocity, vibration, this kind of force. So it should be very sturdy. It is very tedious task. And then there is a current meter arrangement like this. You drill you have to have a manhole to access this interior of the penstock, and usually this is recommended above 1 meter penstock area, penstock diameter. And what we have is minimum 13 current meters, 1 at the center, 3 at 4 arms. 3 each at 4 arms of the cross. It is called cross arm. We have to have a small flat connected inside the penstock and mounted on the these cross arms, 13, 1 at the center and 3 each at 4 arms of this one. This was a very yacht Germany type of current meters were there in CW. We are extensively using for this for flow measurement, but it is a very tedious task. We have to dewater the penstock, shut the plant, dewater the water, weld or fasten these cross arms, fit the current meters, take extension of these wires, connect it to the this plotter where we can have a pulse train, and we, with the use of a planimeter, we can have, using velocity area method, we can calculate discharge. But it needs 1 week's work, almost 1 week's shutdown for measurement of this one. So it is nowadays it is discouraged because of big demand, and in its place current meters, ultrasonic flow meter has taken way, and it can be done without disturbing the system. So ultrasonic flow advantage is that we are not disturbing or disturbing the system. When the plant is running, we can simply mount the ultrasonic flow meter, one at the upstream, one sensor that is usually called a transmitter, and receiver at the downstream side. And with this array of transient signal, we can measure discharge. This is something like a person swimming along the river and swimming across the river. That difference in time of transmission is the measure of discharge. It is proportional to velocity. Okay, here typical requirement is 10D dam upstream length and 3D downstream, and this is the minimum requirement. And if you don't have this kind of straight length in the upstream, we can't use ultra. But there are situations we have used in the very constrained passages also for the purpose of carrying out up RMU, as in Bhadgar, Veer, etc., for the purpose of somehow assess the efficiency to have upgraded turbine in the future. And then there is a Doppler. It is the same ultrasonic flow meter. The working principle is different. Okay. This is how a ultrasonic flow meter looks like. Here it is mentioned. Advantage is stoppage of plant is not required. No head loss of system. Upstream length is less required. Okay, this ultrasonic flow meter is nowadays used in measurement of discharge in a canal, like this situation, permanently. This is one photograph I am showing. This is the water supplied from Punjab to Delhi for their municipal requirement, and this particular arrangement was calibrated by the using a acoustic Doppler current profiler ADCP for Delhi Jal Ring when this was done 4 years back, and there was a dispute in the courts over what is the quantity of water supplied by the supplier, and the dispute raised by the receiver over the quantity of water. Then CWPRS has taken a role as a neutral agency to actually assess the discharge using a ultrasonic ADCP. This is the ADCP. It is something like what is the thermocol, like very lightweight boat, and there is a transmitter at the bottom of the boat that transmits, send a signal, then it gets reflected from the bottom, and it profiles the entire wet area, and volume is calculated based on the ray of velocities taken from one bank to another with the accurate area, accurate height, and corresponding velocity. This is one work we have done for Karnataka Jala Nigam Limited, KBJNL, Bhagya Jal Nigam Limited, KBJNL, for automation of canals. An ultrasonic gate fitted with the ultrasonic sensors, powered by solar, was supplied by some agency to large number of canals for supply of water to different users, agriculture users. And that particular arrangement was calibrated by CWPRS, and it was also tested. Say, this is the arrangement. We can say one type of arrangement. This is the gate. The other one is the that powering arrangement with the solar. So this is how it was looking at the site near Vijapur, Narayanpur. So here we can see this principal secretary having an observation of the arrangement. CWPRS and FCR was also involved in these studies, but we have come to the conclusion that up to an accuracy of, say, 5%, that is expected in this kind of field open channel studies or experiment investigations. It is acceptable for canal automation. This is first time, I believe, is taken up by any state government for canal automation, and with very good modern techniques. We have got each customer of agricultural use has got one password, login type of arrangement, and he can monitor what is his use, what is his charges levied, etc., etc. Okay. This is the arrangement. V-notch for principal. This is specially prepared for calibration purpose at the site. Then field studies for Koina hydroelectric plant we have done in recent time. I'm narrating here that we have got stage 1 and 2, 4 into 70 megawatt and 4 unit into 8 megawatt. So total 600 power generation megawatt. This is a basic what you call baseload plant. The discharge in each turbine unit is 16 meter cube per second, and for, say, nearly 500 meter is the head coming from that Shivajinagar dam, and the turbine type is Pelton. And we have done investigation for this in 1995, 2000 to 2004, and now it is going on 2018 onwards. Recently, last month only, I have been to that site for investigative studies, intermediate water level. Then stage 3, there are 4 units of 80 megawatt Francis type of turbines, and this is a plant at the lower at the lower reservoir or a collecting reservoir at the tail end of the power plant, this 1 and 2 power plant. Even stage 4 also, it's a recent entry. In 1999, it was commissioned, Alstom machines, 4 into 250 Francis machines. It's a huge discharge, 65 meter cube per second. And that is functioning very well. And it is well-known leg tap arrangement done first time in Asia in the year 1999. And it is working very well. And that investigation is going on now for that plant, for all these 18 turbines by CWPRS. Then there is one small power plant, that is KDPHS. This water from dam foot power station scenario, small hydro, 18 megawatt into 2 units. This mainly caters to the irrigation purpose. This ultimately flows to Krishna River. That is this particular, and I think even Kerala is also beneficiary of this water release. And Tamil Nadu, this goes to mainly Andhra Pradesh to agriculture purpose. This is the arrangement, how it look like. This is the stage, this is called a stage 4. That is, this particular reservoir here is the tail portion of 1 and 2, plant 1 and 2. This is mainly a collecting reservoir. This plant of 4 units works basically on a daily and weekly basis collection of water. This is how pressure transfer is fitted. This is in this picture we can see ultrasonic flow meter in use. Field study for kinetic from stage 4, you can see this is the stage 4 arrangement. Runner picture also you can see. See how we measure discharges. I said discharge measurement is very, very difficult. It is challenging. This entire stage, like I think Idiki is also it's underground power plant. This Koina is a totally underground power plant, and you can see this. See, a cave is there inside the power plant, accessible by this. Without any, in this COVID scenario, without any ventilation, we have done our fitted ultrasonic flow meter here in a small cave and monitor discharge. You can see this discharge values and done the experimentation at a different water level. It is proposed that this water level varies at the lowest level 625 meter when the local Koina reservoir level to 660 meter. So we have seen to assess the performance of each turbine from varying from lowest water level, that is 625 to up to 660 at a 10 meter difference each year. This is what experiment is going on, and with this we have to establish the performance of the or degradation. So this is the salient features. Okay, some typical test result is going on. Performance turbine of stage 4, you can see efficiency variation. You can see this is unit number 1, unit number 2, 3, 4. This kind of variation we can see, and we can draw a conclusion with the variation in water levels, and what is the remedial measures required in case of some faulty functioning or degradation. This recently in March, our team has gone to Ukai in Gujarat, and in fact we are leaving tomorrow also for that same power plant for especially leakage measurements. See this here for first time by CWPRS, we have used ultrasonic, that is open channel flow measurement. For usually it is a well-known practice that flow is measured in closed conduit penstock, but away from that conventional method, we have proposed to use open channel, this kind of ADCP. It is an American product to have a profile of Walters tail race, then integrate it for entire area and measure this charge. And this is this particular equipment, that is ADCPs, came to have an accuracy level of 2%. But in this kind of RMU purpose, we are looking at a overall uncertain level of 4 to 5%. Otherwise, it is not a very, very accurate way of measurement. Since no other option is available, we are using this for measurement. This for BIRA also. This for to stand as something like a calibration. We have got our measurement done in close to conduct ultrasonic flow meter. In addition, we are making it in open channel flow bus to correlate the flow measurement options. This is Salal project. We have done 2 years back as a part of acceptance for NHPC project. The turbine is supplied by Voith. Problem was reduction in power output of plant observed when all 6 turbines operated together. 705 megawatt was required to be, it was a plant capacity, but there was a miss of 25 megawatt, 685 only was possible. So an investigative was done, I think sometime in 1995 or so, and we have recommended for replacement of turbine with the changed specifications, and they have implemented, now again tested 2 years back, 2017, and now it is generating 10% more. This was the earlier studies. The turbine supplied by BHL. Now Voith has supplied this one. I think it is the efficiency level at that time was 90%. Now it is 94%. It is a 2017 study. This is the arrangement we have done for flow measurement. Say this the biggest problem here was to climb this inclined penstock and have this one standard length, look for standard length. Somewhere here there was an accessibility, and we have measured, and this you can see here. This is the structure and how we were accessing and doing the work in this one ladder pattern, the intermediate platform. These are the problems. Runner, you can see. Findings of these trains will enable, actually has enabled NHPT to decide on a new runner, and they have done. They have given order to Voith, a German company, and now one turbine was tested in their own lab, witnessed by NHPC people. We have witnessed the acceptance test. It was acceptable. That particular claimed efficiency 94% was possible, much higher than that was realized. And now, based on one test turbine, they are supplying 6 turbines. This one test we have done for Loktak hydroelectric power plant is there were 3 turbines of 35 megawatt each. The head was ranging from say around 300 in and around 300 meter, and discharge was contemplated was 14 meter cube per second. RPM of the runner was 500, penstock diameters 2.3 meter. This is how we utilized ultrasonic flow meter in penstock, somewhere here in a horizontal stretch. It was having a sufficient upstream and downstream length. This is the situation in the bird eye view. Penstock going in a hill terrain. This is the turbine. Photographs. Say this, you know how to evaluate efficiency. Efficiency is power output divided by gamma specific gate, discharge in meter cube per second, head in meter. This gives efficiency. overall efficiency of plants. P is in megawatt, that is a generator output. Here this is, but this is overall efficiency. But usually to evaluate turbine, we have to assume some efficiency of generated, divide the megawatt by the generated efficiency, and come to the turbine and to what is the turbine output. Okay, I hope you are clear. Are you with me? This is the arrangement. Main parameter measurement is discharge, power, the input pressure, then tail race water level variations. This investigation was done in 1998. I'm lucky that I was also part of this investigation. Their problem was that they had 3 units rated at 35 megawatt, 105 megawatt total, commissioned in 1977, inaugurated by Srimati Indira Gandhi, then Prime Minister of India, but they never reached 105 megawatt when using 3 units, or maximum 95 megawatt or 96 megawatt they could get. The reason being the loss of power and higher discharge is that this surge tank was exposing, and we could see the fully exposed surge tank and air pockets engulfed actually a mixture of air and water entering through the surge tanks. When we are asking for more and more power generation, then in fact it was reducing the efficiency. So this was a problem. Then we had a discussion with the supplier, that is BHEL. We had a joint meeting. Then finally we have come to the conclusion that turbine required to be re-rated. It has to be, because with the existing within the surge level design, we can't have 14 meter cube per second as the discharge rating, and it was reduced to 12 meter cube per second. And with new rating of the turbine, a new turbine was fitted in the existing power plant and existing scroll casing. And the earlier results you can see, it was in the range of say 72 when 2 machines are in operation, 1 and 2. And you can see all 3 machines are together. It was further reducing efficiency when we are asking for this, more power generation. But no, one we could say is that the out of all 3 turbines, the unit number 2 was performing better. Okay, this is the final result. The specification was finalized. New global tender was taken. A person, one supplier has fetched the order. It was not BHEL, but some Delhi company of Power Equipment Limited, something like that, with the Russian collaboration, fetched the order. It was tested for new. That turbine unit was tested at LMS St. Petersburg, Russia in 2009, and it was generating an efficiency guaranteed was 93.74, 75% load, that is 75% of 35 megawatt. 100% load 99.46, and 10% overload 94.5. And what they witnessed is similarly it higher than the guaranteed. And in CWPRS we witnessed the test at acceptance test at CW at site, and it was in 2011 I believe. What they guaranteed is 94.916 for all the units. What we found is that it was giving an accuracy of efficiency of 95 odd figures in for all the 3. So ultimately, the discharge is trying to hide. the efficiency now it has increased from 78 to 94. Just imagine more than 15% in efficiency. And this if power also generation from 95 to it could go up to 10% enhancement up to 126 megawatt. This is a individual performance, hydraulic performance of turbines, you can see. This V hydroelectric program we have done recently. We have explored use of current meter for low. As I was discussing earlier, there was no accessibility to the water conductor system, penstock. We have explored in a rough, it is not a lined canal, in a rough canal we have used at the tail recent use of current meters. In a single current meter, we explored the discharge with the velocity area method, and this turbine has gone for RMU with our this figures you can see. So efficiency, what you could find is that 78%, 76%, etc. at different varying power load. In this case, in this case, what I could say that Maharashtra government has approached me for the measurement of discharge and power evaluation of efficiency, but the initial tendency was that to say because it is not possible, there is no access to water conductor system, it cannot be done. But they have requested again, and they have arranged for a site visit. Then we found that only option left, though it is a very crude way, the measurement of discharge in open canal. There we have done somehow. This has made way to go for RMU works, and now they are in the implementation stage with the new equipments. So now, as you are seeing, it's a laborious work to make measurement and then design turbine for existing plants. It's a laborious work, but CFD comes in handy in have minimum trials, have experience at laboratory, then propose. Of course, validation is very essential to really ensure the effectiveness of CFD. These are the CFD aid used for this. I borrowed from Mohit, some Francis and Kaplan machines. This is how we would look like. What we gain from CFD is knowledge about various properties. Say performance we can understand. Cavitation we can have look into it. Stability we can understand. Detailed information flow features like we can see here. It is possible, and we can come to a conclusion with the proper specification of a new turbine. Ultimately, we need to go with experimentation, either with the model studies or with some other data validating this kind of things. Many times model is constructed and an experiment is done, or at the if not possible, at least at the site pure test is required. Okay, these are some of the runs. So in this process is old runner, you have to have a diagnosis, register all the data, assess it, weigh all project related parameters, what are the constraints in the site, what best we can enhance the efficiency, what are the modernization required, we have venues for renovation, all these things, including civil and other aspects. But mostly we concentrate for power enhancement, we mostly concentrate first on generator, where we can change windings and get good upgradation. Second is change of runner or modification of runner or repair to the runner. Then further modification, say in the form of tail, draft tube, etc. So first is register the data, site data, analyze, develop and evaluate suitable standardized modernization scenarios. Here, CFD takes a big role. Then therapy is implement the optimization solution and test, ensure it is actually reached at site with site test. Okay, this is 3 phases of CFD plus execution. So what is you can see blue is the line for enhancement possible for coupler type of turbine. This may be the range of operation. Blue, lower one, and the higher one. This much of upgradation is possible. The pink one we can see. This is here, in fact. Pink one we can see for Francis. There are also 4 to 5% enhancement is definitely. It's most of the time up to 10% is possible when we take into all the components. And Pelton, it is a, you can see this is very helpful. You can see the range of efficiency levels in each type of Pelton. Typically, it is having a lower efficiency, and coupler type of turbines, blue one is having flat efficiency range. It is a gradual variation. So coupler times is good for a good performer. Efficiency expected in a turbine is right. अभी हमको वापस थोड़ा बाद में एक और प्रेजेंटेशन करना है, आप इधर है नहीं इधर okay. Sorry to disturb you. These are the improvements possible. You can see stator winding, as I said. This is the first thing we can look at. 5 to 10% is possible. Stator winding plus stator core, 7 to 15% is there is avenues to possibility. Then this is in generation part, electrical part. See, we can see RMU works in. It was done in our presence only. 4 into 50 megawatt Kopali hydro plants in Assam. You can see the stator windings, armature, everything. We deploying our men for use of ultrasonic plane inside the jungle. Okay. This Badkar hydroplane. Okay. See, I was telling most of the places there are so many constraints here to assess the present efficiency level of Badka hydroelectric power plant. I think 18 megawatt plant in near Pune. We have been asked to do this diagnose before implementation of RMU scheme. We could find that immediately after main inlet wall, there is hardly this much of, say, 1 diameter is possible to have to fit our ultrasonic flow meter. This we explored. It is very, very non-standard practice. Even then, we could get a good understanding of the flow, and we have given our recommendations. They have gone for RMU works for upgradation of power. So this is one set of, we can see draft tube, turbine, etc. that was available in CWPRS for model tests. And this we can see cavitation in Hubbard cavitation in coupler type of turbines, and this Francis unit. So you can see this helical type of snake-like, helical-like, I mean, the tip of Francis turbines. This is in higher discharge. We can see coconut-like Hubbard cavitation. This is the actual photographs taken. Recently, we have completed in the last year, March, we have completed a model study for 4 into 125 megawatt hydropower Kunda pumped storage near Nilgiri for Tamil Nadu. And this is the, we can see the model witnessed by the hydro turbine tangent go here. This is the model. This is the power. This is the pump storage scheme. This is this one pump story. We pump the water to the higher reservoir. This is the higher reservoir. This is the lower reservoir. So it is a both in pumping mode and turbine mode we have tested with all dimensions of intake, and it was found that the turbine intake design was very good, and it is being implemented now. This is one Chiplima hydroelectric project. Recently in November we have done during the thick of COVID situation. This is the this is our Orissa electricity board person, general manager. So this way you can see, this you can say in that Chiplima project, you can see couplant runner, you can see guide vanes, actual photographs taken during implement execution. This is the scroll casing. Water enters through. It is not a mechanical one. It is a civil construction. It is a channel, concrete construction. Water is channelized. You can see this is one man's height. You can see here. People are standing here. This is the fixed guide vanes, and here you can say BHL, my friend, philosopher and guide, VK Pandey, who is there as part of VOIT Delhi here during discussions. This is Barapul hydroelectric plant, Cananore near Iriti. We recently in January 2020, we have done this investigation for ensuring the performance of inlet pipe for Barapul. It was tested, but this particular piece has failed, so there was a difficulty in operation. So then we have gone for inspection and actual hydraulic testing of that power plant, and now it is working all right with the modification of inlet pipe, casing inlet pipe. This is the testing team and their operation. This is the construction, how it looks like. Conclusions. Standard methods cannot be employed always for flow measurement at site. Turbine operators generally do not allow a shutdown for installation of flow meters. That is what I was discussing. So we explore almost always. This is the worldwide scenario. Always, almost always, we explore first use of ultrasonic flow meter. Otherwise, other options. Current meters fitted inside the fence stock is a very good option. Not today, but 20 years early, because there is a physical loss of water, physical loss of power generation during that shutdown period. Then there is a difficulty, large days required for this experimentation, and I know one situation where Kerala government did not give any permission to shut down for testing of turbine lower Periyar. So this shutdown, especially in summer seasons, nobody will allow for the purpose of investigations. So ultrasonic flow metering is very handy. Measurement of turbines is a challenging task given the non-standard flow measurement practice that is prevailing. Ultrasonic flow is a promising addition given its advantages of easy portability, clamp-on mounting, and easy installation with less manpower required. ADCP is being explored for flow measurement where penstock is not accessible for flow measurement. This WPRS is now banking on with its deployment at tail. Thank you so much. I had a very long presentation here. I'm sorry tying you up here for this extended period, even after delaying this start of this for a good time. I'm extremely sorry. Thank you so much for patient hearing. Should you have any questions, I am here welcoming those.
Okay, thank you, sir. So this is time for questions. Delegates, if you have any questions, please ask to our resource persons. He is ready to face all the questions.